Dear students, so welcome back to my video lecture 2 on S block elements. So in video lecture 1 we discussed all the most fundamentals of P block elements. Okay, we started with boron family elements. There we started understanding the electronic configuration of boron family elements, isn't it? What was the general outer electronic configuration of boron family elements? Yes, it was NS2 NP1, isn't it? The general outer electronic configuration of boron family elements is NS2 NP1. Am I correct? Okay. Now we have got to discuss about the next physical properties of boron family elements. Which are the next physical properties? That is the atomic radius. I told you, if you want to discuss about the other physical properties of boron family elements, you should be knowing, you should have a clear-cut idea about the electronic configuration. See, understand this point. Okay, all the boron family elements are exception rich. That means you will find lot of exceptions in boron family elements. You have got to understand lot of exceptions. Each and every physical property will have exceptions. So if you want to understand those exceptions, then you should be knowing about the electronic configuration. Okay, so in the previous video we somewhat struggled in writing the electronic configuration. At least now it is clear, I suppose. Okay, the atomic number of boron is 5, aluminum is 13, gallium is 31, indium is 49, okay, thallium is 81. I told you to remember Bal Gangadhar in Tilak. Okay, so boron is a non-metal which is also a metalloid. Aluminum, gadolinium, indium and thallium are metals. Okay, so I hope you know this. Okay, now coming on to atomic radius. How does atomic radius vary down the group? How does atomic radius vary from boron to thallium? How does it vary from boron to thallium? We have understood this in periodic table. Down the group, okay, yes, down the group atomic radius must increase, isn't it? Okay, so we have understood this. So down the group atomic radius should increase, correct? Should increase, correct? Okay, so what is the expected order of atomic radius? So from boron to aluminium, okay, it increases. From aluminium to gallium, it increases. From gallium to indium, it increases. Indium to thallium, it should increase. This is the expected atomic radius. But okay, the atomic radius of boron family will not vary in this order. No. Okay, this is not the correct order of atomic radius from boron to thallium. Okay, now can you tell me why atomic radius increases down the group? Okay, atomic radius increases down the group. Okay, atomic radius increases down the group because of shielding effect, isn't it? Okay, we have understood all about shielding effect, screening effect, etc. in periodic table itself. Again, I don't want to discuss all those things, okay, because it will drag too much of our time. So let us not bring the same concept again here. Okay, so just understand this. Atomic radius increases down the group because of shielding effect. And what is the order of shielding effect? The order of shielding effect is like this. Okay, s orbital exhibits more shielding effect than p orbital. P orbital exhibits more shielding effect than d orbital and then f orbital. That means to say d orbital and f orbital, will exhibit poor shielding effect. Okay, will exhibit poor shielding effect. Are you getting my point? Okay, d orbitals and f orbitals will exhibit what? Pore shielding effect. Pore shielding effect. Observe here, from gallium to thallium, from gallium to thallium. Okay, so there are, okay, inner completely filled d orbitals, inner completely filled d orbitals. In thallium there will be inner completely filled what? Okay, f orbital, f orbital. Okay, yes, are you getting my point? So in from gallium to thallium, from gallium to thallium, okay, there are inner completely filled d orbitals and f orbitals. Okay, so since there are inner completely filled d orbital and f orbital, we know d orbital and f orbital exhibits pore shielding effect. So because of pore shielding effect, because of pore shielding effect, okay, the outer electron will be pulled more towards the nucleus. Okay, because of what? Pore shielding effect, because of pore shielding effect of d orbital and f orbital, the outer electron will be pulled towards the nucleus. When the outer electron is pulled towards the nucleus, don't you think, okay, the size decreases? Don't you think the radius will decrease? Do you agree with my point? Okay, once again I repeat, okay, so in boron family, from elements of gallium to thallium, there are inner completely filled d orbitals and f orbitals. These inner completely filled d orbitals and f orbitals will exhibit pore shielding effect. Because of pore shielding effect, the outer electron will be pulled towards the nucleus. When the outer electron is pulled towards the nucleus, okay, the atomic radius will decrease. So that means in boron family, down the group, okay, instead the atomic radius increases. Okay, instead of increasing, the atomic radius will decrease. Down the group, instead of increasing, the atomic radius will decrease because of what? Pore shielding effect of d orbital and f orbital. Because of pore shielding effect of d orbital and f orbital. So what will be the what is the expected order? The expected order is supposed to be boron more than aluminium, more than what? Gallium, more than indium, more than thallium. This is the expected order of atomic radius. But because of pore shielding effect of d orbitals, okay, in gallium, indium and thallium, instead of increasing, the atomic radius will decrease. That means to say, so therefore this is not the correct order of atomic radius. What is the correct order of atomic radius? The correct order of atomic radius is this way. What does it look here? Okay, so there is no doubt increase in atomic radius from boron to aluminium. Okay, why? Because there are no d orbitals, there are no f orbital, therefore there is screening effect. Okay, there is s orbital and p orbital will exhibit, okay, larger screening effect. Okay, so because of screening effect or shielding effect, there is increase in atomic radius from where to where? From boron to aluminium. But from aluminium to gadolinium, from aluminium to gallium, what is going to happen? Okay, so in gallium there are inner completely filled d orbitals. Because of these inner completely filled d orbitals, the outer electron will be pulled towards the nucleus. When the outer electron is pulled towards the nucleus, what is going to happen to the size? Instead of increasing, it will decrease. Therefore, from aluminium to gallium, instead of increase in atomic radius, the atomic radius will decrease and then again increases. Okay, but yes, okay, the atomic radius of thallium and indium are almost same. Okay, there is just, okay, a 4 to 5 degree increase, okay, in atomic radius from indium to thallium. Therefore we'll say the atomic radius of okay, indium is almost same as that of what? Thallium. But still many of the textbooks will say, okay, atomic radius of thallium is more than that of aluminium. I hope you got this point. Why there is a decrease in atomic radius from aluminium to gallium? Okay, so why the atomic radius decreases from aluminium to gallium? Because of completely filled d orbitals in gallium, d orbital will exhibit poor shielding effect. Because of poor shielding effect, the outer electron will be pulled towards the nucleus. When the outer electron is pulled towards the nucleus, the size will decrease. Hence, okay, instead of increasing, the size decreases from aluminium to gallium, and then, okay, yes, yeah, then increases. Okay, gallium to indium, indium to thallium. But okay, the atomic radius of thallium and indium are almost same. There is just 4 to 5 degree angstrom. Okay, and no, 4 to 5 angstrom, that's it, change in the atomic radius from thallium to indium. Okay, simple. So can I write this as boron, okay, more than gallium, okay, and then aluminium, and then indium, and then thallium. So please do remember this order of atomic radius. Can everybody remember this order of atomic radius? Okay, from boron, then gallium, then aluminium, then indium, and then thallium. Okay, yes, any doubts with this? So that's all about atomic radius. Now what about ionization enthalpy? Yes, next physical property. What about the ionization enthalpy? What is the order of ionization enthalpy of boron family elements? What is the order of ionization enthalpy? We know ionization enthalpy should decrease down the group, correct? Okay, ionization enthalpy should decrease down the group, correct? Down the group, say yes or no? Okay, ionization enthalpy should decrease down the group as we expect. But okay, there is no regular decrease in ionization enthalpy from boron to thallium. Okay, as expected, there is no regular decrease in ionization enthalpy from boron to thallium. Why? Because of its electronic configuration, because of the intervening d orbitals and f orbitals. We know d orbitals and f orbitals will exhibit poor shielding effect. Because of poor shielding effect of d orbitals and f orbitals, okay, as observed in gallium, indium, and thallium, ionization enthalpy will not decrease regularly among boron family elements. Okay, so what would have happened in other groups? Okay, there is a gradual decrease in ionization enthalpy from top to bottom, isn't it? Okay, here also we are expecting the ionization enthalpy to decrease from boron to aluminium, but because of poor shielding effect of d orbitals and f orbitals, there is no regular decrease in ionization enthalpy. Okay, there is no regular decrease. Regular decrease means what was the expected order? So this is the order of atomic radius, isn't it? Okay, what was the expected order? We are expecting the ionization enthalpy to decrease from boron to aluminium, then from aluminium to gallium, gallium to indium, and from indium to thallium. This is expected, correct? This is what we are expecting according to the general rule. But the ionization enthalpy will not vary in this fashion among boron family elements. Why? It is because of poor shielding effect of d orbitals and p orbitals. Sorry, d orbitals and f orbitals. See, if this is not the order, then what is the correct order of ionization enthalpy for boron family elements? For boron family elements, the correct order of ionization enthalpy is boron greater than thallium, okay, greater than what? Gallium, then aluminium, and then what? Indium. This is the order. You have to follow this order. Why? Thallium has high ionization enthalpy than all of them. Okay, why thallium has high ionization enthalpy? See, I told you, because of inner completely filled f orbital and inner completely filled d orbital, the outer electron of thallium will be tightly held to the nucleus. Since the outer electron is tightly held to the nucleus, the removal of that outer electron becomes difficult. Since the removal of that outer electron becomes difficult, the ionization enthalpy will be more. Okay, so please remember this order of ionization enthalpy. Actually, we are expecting the ionization enthalpy to decrease from boron to thallium, but it will not decrease in a regular order. Okay, it decreases in this order. Okay, boron greater than thallium, greater than gallium, then aluminium, and then indium. Okay, I hope you can remember this. Any doubts? That's great. Okay, yes. Next, let us talk about the oxidation state of, let us talk about the oxidation state of boron family elements. What about the oxidation state of boron family elements? Okay, what is the general outer electronic configuration of boron family elements? It was NS2 NP1. Okay, so we know there is one electron in the outermost p orbital and two electrons in the inner s orbital, isn't it? There is one electron in the outermost p orbital and two electrons in the inner s orbital. Yes or no? That is correct. See, that means the boron family elements can lose this outer p electron and exhibit +1 oxidation state, or else the boron family elements can lose all the 3 electrons of the outermost shell and they can also exhibit +3 oxidation state. Are you getting my point? The boron family elements can lose the outer p electron and exhibit what? +1 oxidation state. They can lose, okay, all the 3 electrons of the outermost shell and they can exhibit what? +3 oxidation state. So that means boron family elements can exhibit what and what? Okay, they can exhibit +3 oxidation state and +1 oxidation state. Okay, boron family elements, please, it's an important point to be remembered. It's a very important point to be remembered. Okay, remember this point. Okay, look here. So I can say that, okay, we have boron, aluminium, gallium, indium and thallium, isn't it? Boron can exhibit +3 and +1. Aluminium can exhibit +3 and +1. Okay, gallium can exhibit +3 and +1. Indium can exhibit what? +3 and +1. Thallium can exhibit +3 and +1. No doubt in it. Why? Because they can lose either the outer p electron, okay, and exhibits +1 oxidation state, or else they can lose all the 3 electrons of the outermost shell and they can exhibit what oxidation state? +3 oxidation state. Am I correct? Yes. So boron +3 +1, aluminium +3 +1, gallium +3 +1, okay, indium +3 +1, thallium +3 +1. But okay, understand the stability of oxidation state, guys. Okay, yes, stability. Understand the stability of oxidation states. Stability of oxidation state. Please understand the stability. Very important. If you want to learn any chemical reactions further, you should be knowing about their oxidation states. You should be knowing about their oxidation states. Are you getting my point? Okay, so understand the stability of oxidation states very well. Okay, understood? See guys, from boron to indium, okay, so +3 oxidation state is more stable. Okay, +3 oxidation state is more stable, okay, from boron to indium. Okay, so from boron to indium, +3 oxidation state is more stable, whereas in thallium, okay, +1 oxidation state is more stable. +1 oxidation state is more stable. Okay, note this point. That means boron, aluminium, gallium and indium, they always wants to be in which oxidation state? +3 oxidation state rather than +1 oxidation state, whereas thallium wants to be in +1 oxidation state rather than +3 oxidation state. So thallium does not wants to be in +3 oxidation state, okay, because it is more stable in what? +1 oxidation state. Okay, so now what is it? Thallium is more stable in +1 oxidation state, whereas the elements from boron to indium, they are stable in which oxidation state? +3 oxidation state. Now my question is, why thallium, okay, wants to be in only +1 oxidation state? Why it wants to be only in +1 oxidation state? Why it is unstable in +3 oxidation state? Guys, understand here. Okay, see, we know, we spoke a lot about this. We spoke a lot about this. What is it? See, in thallium, because of inner completely filled d orbitals, there will be both 3d10 as well as 4f14. 3d10, okay, 4d10 as well as what? 4f14. Understand this, guys, here. See, in thallium, because of completely filled d orbitals and f orbitals, we know d orbitals and f orbitals will exhibit pore shielding effect. Okay, so because of pore shielding effect of d orbital and f orbital, see, these s electrons will be tightly held to the nucleus. Hence, okay, since these s electrons are tightly held to the nucleus, they cannot be removed. They cannot be removed. Okay, so the only options that is left is, I can only remove this last electron. I cannot remove the electrons from s orbital. Why I cannot remove the electrons from s orbital? Because they are tightly held to the nucleus. Why they are tightly held to the nucleus? Because of the pore shielding effect of d orbital and f orbital. Okay, understood my point? Because of the pore shielding effect of d orbital and f orbital, these s electrons are tightly held to the nucleus. They cannot be removed. Okay, therefore, which electron can be removed? I can remove only one electron from the outer p orbital. Hence, thallium can exhibit only +1 oxidation state. It cannot exhibit what? +3 oxidation state. I hope you will remember this. So that means I can say thallium chloride is more stable than thallium trichloride, correct? Okay, thallium chloride is more stable than thallium trichloride. Here thallium is in which oxidation state? +1 oxidation state. Here thallium is in which oxidation state? +3 oxidation state. +3 oxidation state. Okay, see, so that means I can clearly say that these s electrons of thallium, the s electrons of thallium, okay, are tightly bound to the nucleus. They do not participate in chemical reaction. Okay, that means I can conclude that, okay, the s electrons are inert towards chemical reaction. They do not participate in any chemical reaction. We call this effect as, we call it as inert pair effect. What is this effect called as? Inert pair effect. Inert pair effect. Understood? Okay, so what is inert pair effect? Okay, the reluctance of the inner s electrons towards bond formation is called as what? Inert pair effect. So the s electrons will not participate in any bond formation because they are tightly held to the nucleus due to the pore shielding effect of d orbital and f orbital. Therefore, thallium can exhibit only +1 oxidation state. So what is this effect called as? Inert pair effect. So guys, hope you have understood. Okay, so the elements from boron to indium, okay, they can exhibit, they are more stable in +3 oxidation state, whereas thallium is more stable in which oxidation state? Okay, +1 oxidation state. No doubts? Okay, so that's all about the stability of oxidation states. Okay, so I can say that boron exists in +3 oxidation state, aluminium exists in +3 oxidation state, gallium in +3, indium in +3, but thallium in +1. Thallium in +1. Here also in gallium and indium also +3 oxidation state is quite unstable, again due to the pore shielding effect of d orbital. It is quite less stable as compared to boron and aluminium. But boron and aluminium are highly stable in +3 oxidation state. Thallium is highly stable in +1 oxidation state. Okay, so that's it. Now next, what about the melting point and the boiling point? Melting point and the boiling point of boron family elements. Okay, see, we know metals always have okay, more melting and boiling point, more melting and boiling point than non-metals, isn't it? Than non-metals, correct? Okay, always metals should have more melting and boiling point than non-metals. So we know here boron is a non-metal, whereas the rest of the elements are metals. That means to say these elements should have more melting point than boron. But unfortunately, that is why I said there are a lot of exceptions in boron family. Okay, this is one among them. Okay, so of course aluminium, gallium, indium and thallium are metals. They should have more melting point and boiling point. But unfortunately, what is happening here, boron has high melting point and boiling point. Okay, boron has, okay, high melting, okay, has high melting point, okay, than the rest of the elements. Even though it is a non-metal, even though boron is a non-metal, okay, the melting point of boron is more than that of the rest of the elements. Okay, students, we will understand why boron has more melting point than all other metals in the next class. Okay, thank you.